is high. In this video, we will solve the differential equation for the LC circuit. In fact, solving the differential equation itself is not a hard task. The harder task is to form the differential equation. So let's start. Let's first draw an LC circuit. An LC circuit is just an electrical circuit with two components connected in one loop. So these two components are first the capacitor with capacitance C and the inductor or the coil with inductance L. To form the differential equation for this LC circuit, we will use the Kirchhoff loop rule. And before applying this rule, we should assume a direction for the current. The direction of the current, well, I can assume it wherever I want. I can assume it clockwise or counterclockwise. So I will just assume that it is in this direction. So clockwise. Now, what does that implement? This implements first for the capacitor that there are some positive charge here and some negative charge here. So without these positive and negative charges on the plate of the capacitor at these locations to be exact, so the positive is in the upper and the negative is on the lower, without this we will not be able to obtain this current. So because I assumed this direction of current, a positive charge must be on the upper plate and a negative charge must be on the lower plate. Also, the inductor here, once there is a change in current applied to this inductor, there will be an induced voltage. This voltage will be in the opposite polarity. So we will have here positive and we will have here negative. Of course, this polarity will help the inductor to kind of resist this current coming from the capacitor or from the wires. So it's kind of making a current in this direction. Now, we have this circuit and we know the voltage polarity. Now, we have also a note that we need to mention. If my solution at the end gives current positive, it means that it is moving in this direction. And if the current is moving in the opposite direction, then it has a negative sign. But the magnitude will be correct. Now, for a capacitor, we have the following. We know that the voltage or the potential difference between the two plates of the capacitor is equal to Q, the charge of the capacitor, over the capacitance C. And for inductors, the potential difference V is equal to L di over dt, where L is the inductance, it's a property of the coil, and I is the current. So now let's form the differential equation. Let's apply Kirchhoff loop rule. So let's start from this point. Let's name this point P. I will start from point P and go also clockwise. So starting from point P, moving, I will reach and face this capacitor, and there will be an increase, or yes, an increase in the potential, so it's positive Q over C. Then I will continue moving and I will face this inductor, so it will be a decrease in the potential, so a voltage drop, let's say, so it's minus L di over dt, and of course this will be equal to 0 because we will come back to this same point P. Now this is the trick. The trick is in unifying I and Q. Now some people might say that, oh, I is just equal to dq over dt, and that's it. Well, it's correct, but here I is just minus dq over dt instead of dq over dt. Now why is that? Well, let's look at the figure. If I is in this direction, this means that the positive direction of I is in this direction, right? And this implies that the charge of the capacitor is decreasing because there are positive charges literally going out of this plate. So if these are charges on the plate, when we have current I, these charges will be removed and move through this wires, through these wires. So they will leave this capacitor or the plate. Now, in this case, Q decreases while I having a positive, of course, a positive value. So this is why, and of course you can apply it for the case of the case of charging this capacitor, but then the polarities for L will change also. So let's keep things simple, and if you want to think about it more, you can think about it with yourself. So now I is equal to minus dq over dt, and this is the trick. Why is that? Because this current, the one that I assumed, will have a positive direction in this case, or to the right. If it goes to the right, then this current, which has a positive direction, will make Q decrease. There will be a decrease in Q. So yes, I and dq over dt, or change in Q, will have the same magnitude, but they will have the opposite signs. So now we can write our differential equation, Q over C plus L, and multiplied by the second derivative of Q with respect to time, and this is equal to 0. So that's it. This is our differential equation. From now on, we will be working on solving this differential equation, and it's just a matter of math. Now we can rewrite, of course, now we will be solving the differential equation. So we can rewrite this differential equation as second derivative of Q with respect to time plus Q over LC, and it's equal to 0. This is a second order differential equation, ordinary differential equation, and it's homogeneous. Of course, this differential equation is of constant coefficients, and to solve such a differential equation, we can assume the solution Q of t equal to e to the mt, where m is just some constant that you need to find. So the solution will be of this form. Now, if I substitute this solution, I'll write it again. If I substitute this solution here, I will get the auxiliary or characteristic equation. If I solve that characteristic equation, I will be able to get m. So if I substitute this one here, then divide by e to the power mt both sides, I will get m squared plus 1 over LC equals 0, which means that m is equal to, or m squared is equal to minus 1 over LC, which means that m is equal to this square root. And this will be equal to j multiplied by 1 over square root of LC. Now what is j here? J is the square root of minus 1. Why didn't I use the letter I? Because the letter I is reserved for the current here. So I'm not using it to denote the square root of minus 1. I'll be using j. So m, which is this constant here, is of course this quantity right here. But of course we forgot something. We forgot the plus minus signs here. So plus minus. And that's it. We found m. And we just need to write this solution. Of course, this is second order differential equation and it needs, it's of course homogeneous. So there will be two linearly independent solutions. So q of t will be equal to a1 multiplied by e to the power j t over square root of LC plus a2 e to the power minus j multiplied by t over the square root of LC. Here a1 and a2 are constants and they are determined by initial conditions. Okay. Now with some, of course, with some identities, we can rewrite this as a multiplied by sine or cosine, you can choose, of 1 of t multiplied by the square root or over the square root of LC plus phi. Now a here is again a constant and phi here is a constant determined by initial conditions. So if you have your initial conditions, you will be able to solve for them. Okay, now, so here also we have a and phi. Great. So now we found q of t. We solved for q. Now can we solve for I? Yes, we can solve for I. I is equal to minus, don't forget the minus sign, dq over dt. And this will be minus a multiplied by 1 over the square root of LC multiplied by cosine of t over square root of LC plus phi. So I is a function of t, of course, and it is equal to this thing. So this is my I. So we solved the differential equation of LC circuit, and we can find an interesting fact that the current here is having a sinusoidal behavior. Yes, it is cosine, but it is sinusoidal behavior with some phase shift. So now, of course, this is impressive because here there will be zero loss of energy. Of course, we don't have a resistor or any resistance here. So the total energy E is conserved. It is constant. It will not change in time. So we solved and we did our objective of, or we achieved our objective of solving this LC circuit differential equation. The trick about this whole thing is this part, that I is equal to minus dq over dt and not dq over dt.